Good afternoon, everyone. I'd like to welcome you all for the 5 days Emerging Semiconductor Technologies of IoT and AI Application organized by the Electrical and Communication Engineering, SJC Institutions of Technology, Karnataka in Coimbatore in association with Pennsylvania. So it's my immense pleasure to introduce our today's speaker. Dr. S. Sujasa is a designated faculty member in Department of Biomedical at KIT College, Coimbatore. With a strong academic background and the passions of innovation, Dr. Sujasa has been instrumental to advising the research and educations in the field of biomedical. The work has focused to the the gap between the engineering and medicines and create a solution to enhance the healthcare technologies and improve the patient's outcome. As the commitment of educator and a researcher, Dr. Sujasa has significantly contributed to development and aspiring the engineering and researcher. This expertise spans the various domains of biomedical engineering, including the medical device, the innovations, and the biometric informations and healthcare automations. By the forecasting disciplinary tree, the collaborations and enthusiasm, the practical learning, Dr. Sujasa plays a role in the shaping of futures of biomedical at KIT and renowned the institutions to dedicate the academic excellence and social impact. Welcome, you, sir.
Thanks for welcoming me.
So, voice is clear, sir?
I will share my slides.
Right? Okay, sir. Okay, sir.
Shall I start the session?
Sir, I can start the session, sir.
So my screen is visible to all.
Yes, sir. We can able to see your screen, sir.
And thanks for welcoming this wonderful session. My title is about chiplet design for IoT and artificial intelligence applications that will come under the emerging semiconductor technologies for IoT and AI. So first of all, I thanks to my management. They allow me to deliver this section to the other institute. Thanks. And I thanks for Pencil Bits to invite me for this session. Thanks. These are the things I'm going to share today with you. Semiconductor technologies. What is the semiconductor technologies? When it was emerging in the field, and what are the things that was having the advancement in IoT and AI? Key technological advancements, fundamentals of chiplet architecture. So, in this view, there is a fundamentals of chiplet architecture. I'm going to tell you what are the tools, software tools currently used in the market for designing chiplet design. That is a monolithic, apart from the monolithic architecture, how it is to be predominantly available in the market, the tools that was available, and design principle of chiplets, the chiplet integration techniques, key components, design and development challenges, applications in Internet of Things. In that Internet of Things, we already know about what is IoT. So I'm not at all dealing a very brief session about IoT. We'll touch about some points that IoT and applications in AI, challenges and the future direction. So these are all my contents I'm going to share with you over the next 1.5 hours into semiconductor technologies. So we already know what is semiconductor and it was emerged in the year of 1947. And before before the semiconductor fields, we are having the transistor as a media. The transistor that was developed by Murray, that is William Shockley, Walter Pridgeon, and John Burdens. That discovers that brings transistor into the picture in the past 1947. But there is some innovation required for many miniaturization of size, miniaturizing the size, and performance analysis, and we can call it as a resolution, performance, and how it is to be improved in the current scenarios. So that is an historical context. So this legacy technology and the limitation, that is, what are the limitations in the previous, I think is nothing but mainly hardware parts. So here, chiplet, because why I'm telling about the hardware, because chiplet is purely depending upon the hardware miniaturization. It is not deeply connected with the software tools, because right now we are having a number of softwares for designing the architecture. But how we are going to reduce the size of hardware in a single chip, SiC, silicon on chip, how we are going to develop or integrate n number of components. If you are taking a processor, currently n number of active and passive components or integrated in a single in a chip, in a board, you can call it a PCB board, and that we are going to deal with that. But it occupies spaces. But how it is to be reduced? How the spaces are reduced? That will bring our chiplet design. The chiplet, the sizes are reduced and the performance was improved. And similarly, our resolutions will be purely increased. Okay, so these are all historical context and evolution of silicon as well as the chiplet design. Now, our semiconductor devices currently plays a vital role in the communication bridges. Before touching our chiplet design, how it is to be improved in the communication, because currently we are telling about the 5G, 6G, but in all the fields, the semiconductor plays a vital role. So it is expected to keep growing due to variety of megatrends. Likewise, wireless communications, we are having 6G, right? Currently, we are telling about the 6G communications. 6G communications, if we are in touch, then there is a problem in, again, in the size of the components. So that also one of the applications of semiconductors, and it is increased demand for electric vehicles, autonomous driving, augmented AR and VR, augmented and virtual realities, and a number of applications in artificial intelligence. In the coming years, the markets, the mainly focused about not only for the communication, it was improved that performance in automobile sectors. That is, we can simply call it as autonomous vehicle systems. Autonomous vehicle systems. The automotive semiconductor segments is mainly because there is a need for electrification in automobile systems and self-driving. Because why I'm telling you this is, a chiplet, it reduces a very huge size into a smaller size, miniaturizer. Because if you take automotive vehicle system, the component size is very big. But if you are implementing the chiplet, it has totally reduced. Similarly, in biomedical applications, because I am from the biomedical background, somewhat, we are using this chiplet design for rehabilitation engineering. We can simply call it as supporting devices, or we can call it as a self-assistive devices. If a person rehabilitation, you suppose I'm coming because artificial intelligence, if you touch, that will indirectly touch with indirectly or directly also, it will touch with the rehabilitation engineering. So I am going to tell this AI with our biomedical also. So the automotive semiconductor segment is pushed by a need of electrification and self-driving. Similarly, not only for the electrification, the data storage capacity is also very increased. In case if you are using a chiplet design, if you use, the data storage capacity is too much. The computation analysis is also very increased. We are all telling about a deep learning method and machine learning methods. How it is to be improved, that deep learning into our machine learning algorithm. Here we are not at all dealing with any software algorithms for AI. It was purely depending upon the hardware implementation or a hardware remodulations of hardwares. So this upcoming years, the market will be mainly driven by the automotive, computing and data storage and wireless industries. So in wireless industries, we simply called as IoT, because in this topic, we deal with artificial intelligence and IoT. IoT, we define this in terms of a cluster of networks, cluster of sensors or cluster of networks. It can be grouped together It was grouped together from various distances, and that data is to be analyzed. So how it is to be analyzed with the help of a chiplet-based designs? How the sensor data are retrieved? What is the data manipulation rate? How the fast it is to be retrieved from the remote area? These are all to be analyzed before designing the chiplet. So the chiplet was also used in IoT designs. Photonics. Photonics, we already know about optical illusion methods, and we are using photons for transmitting any signals, like our fiber optic cable also. Photons to be transmitted from a transmitter side to the receiver side. That applications also we need a computational analysis. There also we need a memory system. How the memory size to be reduced by using a chiplet. So the memory size is to be reduced. Our hardware parts also to be reduced if we are using a chiplet-based method. So in short, what we understood from this slides, instead of software manipulation, only with the hardware, the performance is too much increased. So applications of chiplet, if we are using artificial intelligence and IoT, these slides deal with the application oriented of where our AI and IoTs are mostly used, like power electronics. In power electronic systems, if we deliver a power from, if you are using a boost converter or buck converter, how the converter amplitude is going to increase? That is purely depending upon the controller sizes. So this is the power electronic size. So applications in power electronics. In that power electronics, we are having the power devices and IC. So semiconductors, wherever we are using, we are instructing the word semiconductors. At that area, the chiplet is to be most important. It's a predominant. It plays a predominant. So MEMS, sensing and imaging, is one of the applications. Micro electromechanical systems, sensing and imaging. Because in previous slides, I told about automotive systems. In any automotive systems, we need actuators for controlling the operations. Actuators is nothing but a simple piston movement. So that size also to be reduced if you are using this chiplet-based design. So semiconductors from materials and devices to circuits, packaging, and modules, or we simply call it systems. So MEMS applications, artificial intelligence and IoT is used in a sensing and imaging system. There we are using the chiplet for miniaturizing the hardware. So we are using there is an applications of artificial intelligence and machine learning, sensor data fusion. This is the most important fusion algorithm for retrieving the data. Fusion algorithm is most important. Data fusion, photonics, lighting, and display. This is one of applications. RF and communications, RF and wireless communications. Memory also, instead of RAM and RAM, we are having the RAM for storing. How the non-volatile memories are emerging. So these memory systems also to be breakable by means of implementing chiplet design. Advanced packaging systems. If you reduce the size, the packaging system is drastically changes. So advanced packaging, and overall, this application, wherever the applications we are using, the materials chosen to be most important. So materials and substrates. Instead of silicon, we are having the composition of materials also there. We'll see that materials. So this is about this slide. So the semiconductors are powerful brains having modern technology applications. Some applications to the different sectors. Semiconductors plays an important. So what are instead of silicon, what are the materials available for fabrications? Is nothing but a germanium, gallium arsenide, indium phosphide. These are all some materials having the unique properties, which is having high-speed data communication systems. So instead of using silicon itself, we can use a germanium, gallium arsenide, and indium phosphide. The most used semiconductor material is silicon. We are using in monolithic algorithm also for fabrications. So these chips contains multiple transistors. So for instead of multiple transistors, how the transistor is to be inbuilt in a single platforms. That is the main motto of a chiplet. semiconductors and material that has, we already know about the principle of semiconductor devices. So it can be controlled and modified by introducing impurities or defects into the crystal structure of the material. If you disturb the crystal structure, it is to be changed. So for a brief understanding, I will show one videos for 1 minute. That is a 1 minute video. You just to see about what is the exact of. I think now you understand what is the exact motto of chiplet design. So we are not dealing with the algorithm for developing software tools. Instead of algorithm development, how the hardware part is to be restructured, and how, because in feature, again the SIM card is, there is no physical SIM card. There is no physical contact SIM card. It was again we will come back to the whole 10 to 20 years back. Again the same phone, but in a modified structure of phones without SIM card, with the enlarged communication bandwidth. It is to be upcoming. So these things are there. So importance in modern applications. This plays a vital role in AI processing capabilities by providing the necessary computational power for machine learning and complex algorithms. So for these two, machine learning and algorithms, instead of this algorithm, there is a structure-oriented modifications. The role in IoT devices. We are already, again, I am stretching you the definition for IoT devices, which is nothing but Internet of Things, which is nothing but cluster of sensor networks, which is to be mounted at different places, and the data is fetched continuously without any interruptions. So at that, because n number of IoTs are placed at different, n number of sensors are mounted in the sense, the data, that is a noise chances to interpret with this IoT signals. So how it is to be reduced? That also by means of applying filters. That filter also to be reduced in sizes by means of using a chiplet. I will show you the algorithm for what's the procedure, what is the rules for developing this chiplet designs. So role in IoT devices, integration into consumer electronics, like our hand-on laptops, tablets, having a better performance. By using a chiplet, it's having a better performance, power efficiency, and miniaturization. So these are all important in modern applications. The technological advancement. So if you take a technological advancement, I'm telling about nanotechnology. Nanotechnology, currently we are seeing about for the last decade, and nanotechnology is coming here. For in nano, if you are using the nanotechnology fields, plus there is a chiplet also to be plays an important role. So nanotechnology in semiconductor fabrication, quantum dot technology, photonic crystals. So in case of a nanotechnology, it enhances again the performance and reducing power consumption in electronic devices. In quantum dot technology, it improves against display technologies in solar cells. And photonic, it is increasing the communication, enhancement, the communication technologies, and improves the efficiency of photonic devices such as sensors and lasers with advanced manufacturing techniques. So technological advancement, which is nothing but a digital ecosystem, sir. And a major impact on the semiconductor industries. That was replaced by means of systems on the chip. So that's why SOC is increased, because if you take semiconductor systems, in that the digital systems, we are having a n number of data or n clouds. We are going to handle this cloud data. So we need a SOCs, increasing the number of semiconductor intellectual property cores. So next one is the demand for high performance memory systems. I already shown you here, the memory system is, in that memory also, our chiplet design plays an important role. How the memory, that is components to be reduced by increasing their efficiencies. The memory systems. Historically, there is a strong investment in chiplet design. Current scenarios, Texas, they developed a very good prosthetic and orthopedic. In case of medical devices, they invested a good investment for developing chiplet designs. There is tools available for, normally we are using Cadence software for these things, chiplet designs. So next, roadmap of semiconductor transistors. You just see here, the year of 2003, the size is around silicon germanium, stained silicon is around the size of 90 nanometer, but now it is reduced to 3 nanometers. How drastically the size of the devices was reduced. This is the major part of chiplet designs. The chiplet design now, it was totally reduces all the components and integrated the single chip levels. So chiplet design plays a vital role. The new materials and compounds we are here, they are normally used as a graphene and 2D materials, and silicon carbates and gallium nitrates, because these are all having a high power and high frequency electronic circuits. That is a high communication coverage, high bandwidth. So and also it's having a good electrical insulating properties and thermal and mechanical properties. If you're dealing with any thermal and electrical, normally electrical properties, some devices, not most of the electronic devices, it is to be, there is a need of thermal runaway. So here also, there is a reduced thermal runaway or heating losses there. So by means of using graphene, silicon carbates and gallium nitrates. So these are all new materials and they are used now. And apart from that gallium nitrate, that is we are having the gallium nitrates. Here we are having the pyrite also. Pyrite is nothing but rare earth metals. We simply call it the cadmium telluride, which is widely used in solar cells. Normally they are used in solar cells, but it has a limited supply. But now it is abundant, inexpensive, not non-toxic. So now, apart from that graphite, they are using pyrite. Normally we can be used to replace with the cadmium telluride. Design innovations. Power consumption is very reduced power consumption. Processing speed is high. Enhanced integration with MEMS. So these are all some of the innovations. So normally, if we are going for any updated version, we first think about the cost effective manner, and next one is the speed, performance level of any devices, resolutions. These are all some of the basic factors to be considered while approaching any new algorithms. The increase of processing speed, enhance the integration with the MEMS. So MEMS is nothing but a micro electromechanical system. Normally it was used in actuating element. There the piston is moving to and fro for improving the speed performances. So it is normally by combining mechanical and electronic components on a single chip. So micro, electro and mechanical systems. The semiconductor industry symbolizes swift technological innovations. But the ongoing technology, they need a better performance and superior productivity. In the case of I already discussed about this point, operating cost to be very low and productivity must be increased, and high performance, they need a high performance. So these are all approached by the Texas while implementing chip-based design for biometric, there is a biomedical applications. Also, there is a communication applications, microphones, phones are there without having anything. They are without having any physical SIM card. They develop the systems. So the semiconductor industry is progressively more solution centric, and decreasing time to market has become one of the most critical priorities. Here, we already saw about the 5G communications or automotive segments, Internet of Things to intelligence, right? Artificial intelligence. that plays a vital role in communication systems, automobile systems, and there is a medical systems. A lot of things they to be used. So the chip for semiconductor fuel technologies enriches the lives of individuals and make business run effectively, smarter and faster. So these are some of the advantages. In case of assistive devices, if I take application of artificial intelligence in biomedical, that because a chiplet is going to implement for AI, if AI is used for self-assistive devices, then there is a need of long-run devices. If the device is not to be performed, then there is a problem in that. So there is a need of improving the devices capabilities. That also to be there effectively, and it is to be smarter and faster. Here, Internet of the outlook, it is around 20. It is from the economic ET. There they mentioned here 2019 to 2021. At that time, they are having the level of around 3.8 Internet of Things. Now it is to emerge in all fields. IoT, wireless communications like 5G telling, automobile sectors, artificial intelligence, cognitive is around 3.3. This is the outlook of various segments in different applications. Medical devices, and we are having the power technologies, personal computers. These are all some of these factors indicate how it is. It is the last 4-year records. How they are 2021, they are saying now the 2025 it is going to chiplet design. So a drastic movement from 2021 to 2024. If we are running from these 4 years, and now the trend is around the chiplet design for improving the speed performances. Overall about IoT, I already mentioned you about IoTs. The term refers to the interconnections of devices and systems through the internet, allowing data exchange and automation across various applications. So across the various applications, how the data is fetched and how it is to be retrieved and how it is to be logged in and how it is to be performed. So these are all main factors. Now not only for Industry 4.0, now they are coming around Industry 6.0. At that level, they increased. Industry 6.0, if it is coming, then the approachment of different applications is drastically increased. The evolution, IoT has grown from simple wearables to complex systems, managing entire smart cities, driven by advances in technology and connectivity. So evolution of Internet of Things. So importance in IoT, again, it comes around the connectivity, efficiency, and scalability. Connectivity, it is going to connect a multiple network across the distance, and efficiency enhances resource management and operation processes. It reduces the waste and improving productivity, automated and data-driven decisions. And scalability, enlargement of size of the components, scalable devices to any applications. So that is without compromising performance, how it is to be improved, how the data is to be improved. So these are all importance of IoT. So IoT, the importance is connectivity of various sensors across the distances, efficiency, and scalability. So now this is the evaluation of more up to how the monolithic IC sensors, IC devices to be. Future, this is a monolithic 3D IC, heterogeneous. Starting from this SIP, this is around 1998. Now the future is around monolithic 3D ICs. Because here also we are fabricating only for, we are manufacturing modification only for hardware devices, not for its. They are dealing with not software, hardware devices. At heterogeneous integration after that, here the ultraviolet density. 2016, 8 years back, before it is a ultra high density, but now it is to be a monolithic sensors with a chiplet design. So these are all some design solution like schematic driven multi PDK devices, which this is the architecture. Simply we can, I am inserted. This is how it is to be fabricated from a single layer to multiple layer systems. Now chiplet, you just see a chiplet layout is very small. This is a multi-layer. That multi-layer is obvious to be integrated in a single chip. This is the chiplet. So this is before a chiplet. There is a software to simulate what is the result, accuracy of that devices. So this is the chiplet devices. So just to see a single chiplet, instead of having a multiple transistor or multiple devices, a single device is how it is to be performed. Chiplet design and its principle. The chiplets. This is the name itself. It indicates a modification in hardware. It's a way to build a system on chips, SoC. That will improve our productivity levels and cost reductions. If we are dealing only with traditional system, and compared to the traditional system, chiplet, it reduces the cost as well as it will yields the productivity more than 40%. So it partitions the chip into discrete elements and connects them with the standardizing interfaces, allowing to meet performance and power sizes and cost challenges in 5G, 6G or virtual reality field. So what it does, it divides the chip into discrete elements. And after that, it connects all them in a standardized interfaces. Unlike monolithic system on chips, chiplets, it enables an open ecosystem for modular components that can be reused, and customized. It is to be customized. That is on comparing with a monolithic. SoC is the build system on chips. It increases the modular components. It was enabling the users to define itself. The next one is it's a small, very small. Already I told about the nanotechnology, and that nano field also they should be used. Chiplet is a small modular chip. It performs specific functions. What is it? A chiplet can be a processor core, a memory block, IO driver, or a signal processing unit. It may be anything. It may be a processor, it may be a memory system, it may be a driver system, or it may be a processing unit. So it can be designed to be used in a chiplet this architecture in which multiple chiplets are connected through a standardized high-speed digital interface to form a complete system on chip. So in basic, how the system performance, how the cost reduction is to be done in the sense, without understanding chiplet, we can't do anything. So then what is chiplet? It divides discrete elements, the chip into a discrete element. And there is an interconnection through the standardized interfacing units. That's all. That is a chiplet is nothing but it divides, it splits. It splits n number of components into a discrete elements and then interconnections with the proper networking platforms, or we can simply call it as interfacing units. That will plays a vital role. And like this only, it divides n number of simpler components, and there is an interconnection through a standardized interfacing units. Just to see in this slide, it creates a complex and powerful SoCs by mixing and matching different functions and technologies to create a customized system without having to fit all the components onto a single monolithic chip. It can be divided into discrete elements, all the elements to be based in on-chip platforms. So that is a SoC platform. So these are all different, these yellow line and red line, and these are all indicating the interfacing units from one components to another components. So these are all some simpler structures of chiplet. So what are the tools available for designing a chiplet-based systems? It's a W3650. These are design platforms like simulator. Previous slides is by means of using PHY simulator. Cadence integrity, 3D IC platforms. Soda synthesizers. So these three are primarily most of the researchers, they are undergoing these things. And here, Cadence also plays a vital role. It is a platform for designing multiple chiplets. It includes a multi-technology database, analysis tools, and it's having a floor planning and implementation capabilities. So, system requires EDA, that is automation, electronic design automation tools, to analyze their thermal layers, integrity, signal integrity, and power integrity, and physical connectivity alignments. So before that is surveying any design softwares, we are supposed to know what is what are the EDA system to analyze these parameters like thermal layers, integrity system, like in such as signal and power integrity, physical connectivity alignments. So tools for designing chiplet-based systems. This is the Keysight W3650B. This is nothing but our physics simulators. And next one, Cadence integrated 3D IC platforms, soda synthesizers. What are the takeaways about technologies? It reduces the development timelines and cost. Also, is opposed to monolithic chips. It enhances performances, reduces power consumptions, and improves the flexibility, making them a revolutionary advancement in semiconductor technologies. So, what are the takeaways? Takeaways nothing but development timelines and the cost. It is opposed to monolithic. And, also, the adoption of chiplet standardized for seamless integration of chip with SoC platforms, opening up new possibilities in computing and technology applications. Therefore, a simple application, this is nothing but one of the monolithic platform replaces with chiplets. How it is to be replaced? A simpler components. So these are all some key points. With chiplet technology, multiple chiplets can be mixed and matched into a larger chip. So we already know what is a chiplet. It is divided into digitalized components. That is, and now it is to be, and also it is to be interconnected with the different standardized interconnection units. So mix and match into a larger chips. Modular chips capable to shape a comprehensive chip on. And also, to create a singular circuit, it needs a miniaturized hardware tools. It is enough to develop. So this is with chiplet technology, multiple chiplets can be mixed and matched into a larger chip. So if you need to perform a unit of a processor, how the processor, what are the components required, how it is to be integrated, how it is to be fabricated, and that unit. And next one is our power supply units. And next one is the processor units. Each task can be restructured into a single platform, single chips on units. So trends and forecast. Recently, it dominates the chiplet dominates the very high landscape of computer technology. From the communication side, it was increased up to the level for defense. Defense also, the Tesla, they recently they launched a system for military applications. That also there, we'll share that. It becomes evident that this trajectory is poised for a transformation as time advances. Experts anticipated the widespread adoption of specialized chiplets. Since any researchers, what's their first initial requirement is to reduce the cost with high performance is nothing but by using chiplet, it is to be achieved. So in the upcoming years, the hardware structure is to be restructured. So presently, the market for heterogeneous chiplet integration is experiencing rapid growth. Okay. Apple's Ultra chip introduced in March 2022 itself. Now, technology trends, and we will show later. So now here, if you see, this is the monolithic approach, and this is the chiplet approach. The yield is only 66.7%, but now it is 97.3%. If we compare the cost and the risk factors along with the performance, when compared to monolithic approach, chiplet approach will give see here design for 16 chips and produce 15 chips. And now low cost and risk factors, and here a higher cost and risk. But here we just see here the 16 pairs here. These are the matrix they formed for developing by use of chiplet approach. So when comparing these two, chiplet approach and monolithic approach, the yield of chiplet is around 97.3%. One more video I'm going to share with you actually. Okay, it's not that. It's not for that. It's systems. So at the end of I show that. Chiplet-based architecture design. How the architecture about the chiplet-based design. Here we see this is the chiplet. These are all chiplets. These are all chiplets. And now this is nothing but a silicon interposer. And now this is the link of tile links. So these are all tile links. And now this is the NOC links. And now here you see this much area can be reduced. We need a buffer systems, and we need a mux for multiple access. If you need different types of inputs, there is a need, and shift and adding purposes. And this is the architecture. Now I am going to add these devices through a node. How it is to be integrated into a pooling systems. So this is the pooling systems, and this is nothing but a multiplexer units for this. Because if we are having a n number of input channels, inputs, how it is to be integrated in this input. So all these things deal with a chiplet-based architecture. This architecture deals with the three things. Now I am going to architect this. There is an n number of nodes, and again the n number of nodes are connected through a polling systems, and we need a sampling and hold for retrieving the data. So these three are the most important, and now this implies the chiplet. And now this implies the interposer. Interposer which retrieve the data through a sample and hold techniques. And after that, it is going to eject suitable outputs. So this is the architecture for chiplet-based. So processor in memory systems, it actually is a deal. Initially, I told you deep learning into a machine learning algorithms. Here, the deep learning algorithm, emerging deep learning workloads, it uses a 152 layers, consists of millions of parameters. The fabrication cost to be 2.5D systems integrating PIM system chiplets connected to a network on packages. That is nothing. Here, the network on packages, this is all network on packages. This is all network on packages. After that, what is the fabrication? It is on network and how it is to be packaged. After packaging, how it is to be fabricated. So this is the layer. So however, several scale scenarios, they use a DL workload leads to intercepted data volume. How the data volumes are increased by means of a NOP topologies. This is the NOP topology. This is the NOPs. So how the different data volumes are increased by means of these things. Layer is nothing but we're having a package substrates, glass interposers, and a sensor, and there is a memory systems and amplification. So initially, I told all these things. Packages most substrate first layer, and then glass interposers. Apart from there is above there is a illusion, so optical illusion, and there is the power amplification. This is memory units. Here, this is heterogeneous integration. In heterogeneous integration, starting from PCB to SOC, again SOC to SIC. There is a PCB to SIP benefits. What are the benefits? Smaller footprint, simplification, higher bandwidth, lower power. So again, SOC to HI, there is a high benefit, which is something but reduce cost, shorter time to market, larger than reticle size designs, more flexible. So this is a heterogeneous integration. This is the cadence. So this is a chiplets cadence. The cadence they are using substrate, package substrate, interposer, image sensor, amplification, and the 3D memory systems. So I already told about the communication. This is nothing but there is no SIM. There is no SIM. Chipless, SIM-less based communication channel. So eSIM is a digital SIM card that is embedded in the devices. As software, it is like as a software. There is a universal integrated circuit card, UICC chip. It allows user to activate a cellular plan from the carrier without using a physical SIM card. Without using a SIM card, how the sender is going to access the data. So UICC is nothing but a smart card that stores the international mobile subscriber identity, also a cryptographic key for mobile devices. So with the help of UICC, eSIM, nowadays 2025, after 2025, we are also expecting eSIM in a wide range, eSIM. Modular design, its flexibility and scalability. Again told you, flexibility and scalability is nothing but modular design, allows for flexible upgrades and the scalable solutions, enabling efficient adaptation to diverse requirements and minimizing redesign costs. So modular design and also efficient resource utilization by partitioning resources effectively. That is, if I want to split the hardware components, it is going to partition it. So modular design, it helps optimal performance and efficient use of resources, enhancing overall system efficiency. Normally, if you go for any advancement, we are looking for flexible, whether it is a flexible components, whether it may be a scalable devices, and the next one is efficient devices or not. So these are to be approached by the chiplet designs. Interconnect technology, this will comes under IoT, so interconnect technologies. So different types of interconnects, including electrical, optical, and wireless things, are very benefit in terms of speed, power consumption, and integration complexity. Performance implications, interconnect technology choices. That is normally we need interoperable devices. It is to be best example for interoperable devices. It influences latency period. There is a good wide range of frequencies, bandwidth allocations, and overall energy consumption. So these are all performance implications of chiplet design. And the power and thermal management. So power and thermal management already mentioned in the previous slides. These two are most predominant factors of designing any hardware restructural devices. So power distribution strategies is having a efficient power distribution strategies. It ensures reliable operations, also reduce power losses, and enhances the performance of chiplet-based systems. Thermal challenges and solutions. Addressing thermal management challenges, it is crucial for reliable operation because any electron devices, it is having heat loss components, and that also to be taken into consideration. It involves techniques such as improved cooling solution and heat dissipation materials. So next case is the efficient consideration. Designing for energy efficient. If we are considered energy, then it minimizes power consumption and maximizes performances, contributing to eco-friendly as well as cost-effective chiplet-based systems. Power and thermal management. Applications in IoT. Real-time data fetching systems. I already told you some of the applications like biotelemetry system. In biotelemetry system, doctor is in one places, patient is in another places, and these two sender and receiver are to be aligned with one common platforms. Although in sender and receiver, a components, they need a memory system, they need a processing system, they need a there's a transmitting antenna, they need a receiving antenna. So these components are to be reduced in size, then the utilization is very good. So that's why chiplet all used in biotelemetry also. So in that cases, if I'm going to implement sensors, fetching of data is most important. So fetching a data and logging it to the another places is played by this chiplet design. So low latency communication chips. So low latency communication, it facilitates rapid data transmission between IoT devices and the servers, ensuring timely responses and efficient system. Latency. What is latency? Do you define our latency period? The processing time. If I'm going to send a signal, how fast you are approaching the data, and how we are going to respond to that signals. That is, we simply called as a period of transmissions. How it is to be transmitted from the sender side, and again how I am going to respond from the receiver side. So that will greatly improve by means of using chiplet designs. Energy efficiencies. So low power IoT sensors. So low power IoT sensors are designed to maximize battery life by consuming minimal energy. Ideal for long-term deployment in various applications. Energy efficiency is most important. Energy harvesting technologies, battery management, semiconductors. These are all where we are looking this energy efficiency. These slides deal with energy efficiency from different cases like low power IoT sensors, energy harvesting technologies, battery management, semiconductors. These are all good good efficiencies, better efficiency. So because if you are using an IoT, some sensors they are having a signal and power cable in different lines. In some sensor, they are having a signal and power lines on the same lines. How it is to be distinguished and how the components are fetched. How the components send their signals and receive the signals. So signal and power transmission lines are properly guided by this chiplet designs. So this is the energy efficiencies. Applications in AI. This is a processing unit, graphical processing units advancement for artificial intelligence. So this is nothing but 20 to 30 words, how it is short time period, how the AI search engine is working. Also, apart from that, FPGA utilization in machine learning. This also significantly enhances performance and power efficiency. And digital neuromorphic chips. Neuromorphic chips is nothing but tasks such as pattern recognition and sensory processing units. Sensory processing units, if I am going to deal with the EEG signal, that is we can encephalograph, we are having a 10 to 20 electrode system. So these 10 to 20 electrode system, there is a need of chip. Now, how that chip used to, that is the hardware nature of such a 10 to electrode placement systems are replaced. Because while dealing with the EEG system, you see sensitive signals compared to ECG, because ECG always it is showing a PQRST, because it is a systolic and diastolic action. But our brain, it is having it is not to be a systematic signal, it is a random signal. It is always to be fluctuating randomly. So how far we are going to approach that signals? By means of chiplet. How the chiplet is to be incorporated in that 10 to 20 electrodes. That's why I already told this plays an important role in the biomedical and biotelemetry system also. Brain-inspired computational architectures. Data center optimization. So in data center optimization, cloud artificial intelligence processing, semiconductors, heat dissipation techniques. So cloud AI is nothing but how the data centers are retrieving the data, how it is to be handled the data, how the massive data are to be analyzed. So these are all cloud AI. And heat dissipation, it drives, that is a AI-driven data centers, is preventing overheating and ensures sustained high performance. Challenges and future directions. Physical limitations of miniaturizations, economic constraints. So physical limitations of miniaturization, which is nothing but reducing the size of semiconductor components. It encounters physical barriers such as quantum effects and heat dissipation challenges. And economic constraints, it becomes economically unfeasible due to increased cost in research and development and the rising expense of equipment, scalability issues. Cyber security concerns, vulnerability in semiconductor devices. Many semiconductor designs have inherent security flaws that can be exploited by attackers to gain unauthorized access or disturbed function. Because if you are dealing with IoT, we need a privacy and security algorithms for properly watermarking that. So that's why encryption data protection, and it ensures the data to be encrypted at all stages during processing, in transit stages, and at rest. This is critical for protecting sensitive information from breaches. Secure boot and trust zones. That is creating trust zones within the device itself ensures that only authenticated software can run. prevents malicious code execution. The cyber security concerns. Environmental impact. It deals with e-waste management, sustainable manufacturing practices. And also, we follow the regulatory authorities, responsibilities and regulation, corporate responsibilities and regulations. E-waste management. If you are dealing with any research work, you can deal with this e-waste. E-waste is most playing because we are having a decade to decade or once in 5 years, the technology is reversed. Because if we are going for chiplet, what about the previous edition, what we are using right now is totally vanished. So by means of handling such a electronic waste, that also a good research area to do that work. So proper disposal and recycling methods for electronic waste are essential to minimize environmental damage and recover valuable materials. So that is a e-waste. Sustainable manufacturing practices. So improving again, such as reducing chemical usages and improving energy efficiency is vital for reducing an ecological footprint of semiconductor productions. Corporate responsibility and regulations, environmental. This some of the things also. So I conclude this section at the what I say to this environmental and impact. So any questions?
Is revolutionizing AI. Imagine breaking down a monolithic chip. Hi, everybody. Hope you're all having a great morning. As Elon
If you are having any doubt, just ask. Any doubt, you can ask.
with an FPGA, IO chiplets, and hey, let's put in a machine learning accelerator on that thing as well. So we kind of have this chiplet-based functionality, a lot of different kinds of blocks, but a little bit different capability. And they can build this, I can build this today, use that great advanced package technology, and have wonderful interfaces that line up perfectly. And, ideally, hopefully, every interface has a common link layer so they can communicate with each other. Another thing that I find really fascinating is, can every interface have every link layer for die-to-die interconnect? We do things like that to make this work and enable an open chiplet economy. Now, the problem with this kind of design, even if we solve link layer communication issues, is reuse, right? So let's say I go from that great scalable design that has all that function, and I want to make even bigger processor, big scalable processor system. The minute I do that, is if my die weren't all exact dimensions in my system, the IO chip gets kind of disconnected. It's not going to work, right? So, well, if I want to make a new processor, I got to make a new IO chiplet, which is a bit of a problem, right? We invested a lot of money in making that. Building a whole new one just to get some, I'd say, variation in the function of the chiplet-based system is a problem. Now, there's a solution to this, and I think this was kind of alluded to in the earlier presentation, where you could just tell every chiplet it has to be the same size, right? So unfortunately, in my original system, if I make every chiplet the same size, let's say we pick the biggest one as the least common denominator, I end up wasting a ridiculous amount of space for some of the function, right? We need to be able to connect things together that have varying capability, varying function, or in different technologies. And there just isn't a clear way to make that happen. So what I'd like to recommend we start thinking more and more about as an industry is building chiplet-based systems that have a little bit of freedom. As Elad alluded to, most advanced package interconnect and IO that's developed to support advanced package interconnect, you go a couple millimeters maybe. But I'd really like to see, in order to enable an open chiplet economy, a way to allow chiplets to really plug and play by just loosening things up a little bit, making interfaces that can go a little bit more distance so that we've got capability to, as long as we fix link layer issues and we can communicate with each other, be able to build these plug and play systems. Now, the downside is this isn't perfect, right? We waste package space. We're probably going to waste power, right? A lot of interfaces that.
Last year they told about the chiplet-based design, but right now the products are to be launched in most of the countries. So this is the trend prevailing in that. Any doubt, you can ask me. Thank you to all.
Sir.